Okay, let's try this problem. Calculate the acid dissociation constant, the Ka value, for a 0.010 molar solution that is 5% ionized. Okay, so we have a weak acid here. It's only a little bit ionized, not 100% like a strong acid. Whenever we have a weak acid, the plan of attack, put the acid in water, ice it with a Ka. So let's take this weak acid. I don't have a formula, so I'm going to use the generic formula HA. We're going to put this acid in water, allow it to dissociate a little bit. It will generate the hydronium ion and the conjugate base A-. Now let's go ahead and ice table it. The initial concentration of my acid is 0.010. I write that in for the initial, 0.010. Before dissociation, we don't have any hydronium and we don't have any A-. So we know this reaction is going to progress to the right. We're going to dissociate a little. Well, how little? Usually we would call that little bit minus X, but in a percent ionization problem like this, we know how much comes off. 5% of this initial value is what we need to take away. So let's go ahead and use this formula or calculate exactly what we're taking away. I'm going to move this for a second. We know that we are 5% ionized. So if we look at that ionization formula, I'm gonna rearrange this formula to solve for the amount of H3O plus that we generate, add right here, which is also equal to the amount of HA that we take away. So basically, if we rearrange this equation for H3O plus, I'm gonna multiply both sides by my HA. So the percent ionization multiplied by the initial concentration of the HA acid will now equal the H3O plus times 100. We have H3O plus times 100. Let's actually bring the 100 down here right away. The percent over 100 times that initial concentration gives me the amount that breaks off. So 5%, 5 divided by 100, that's what percent means, 5 per 100, multiplied by the initial concentration of 0.010 gives me a concentration of H3O plus that is created or that breaks away from my acid. That H3O plus in this case that I generate, if you go ahead and do this on your calculator, it ends up being 0.1230 zeros, 5 and a 0. That is the molarity that we generate for our acid, for our hydronium. So I'm going to generate 0.00050. I'm going to generate 0.00050. I'm going to take away 0.00050. Now at equilibrium, what we're left with is 0.00050, 0.00050, and when you subtract these and cut it off at the thousandths place, 3 places beyond the decimal, this essentially stays the same. It does not significantly change. So now we have our equilibrium values. We can use those values to go ahead and find the Ka, the acid dissociation constant. We're going to take 0.00050, that is multiplied by itself, so squared, all over the original acid concentration of 0.10. And when we go ahead and evaluate that on our calculator, we get a Ka of 2.5 times 10 to the minus 5. And that order of magnitude is very typical of a weak acid. I hope that helps. Take care.